in 1054, which is just a great date, recorded by Japanese and Chinese astronomers. And the textbook I use also says in an Arabic medical textbook recorded this. This picture right here is about 6 light years across. The orange filaments are scattered remnants of the star, consist mostly of hydrogen, blue in the filaments, neutral oxygen, green is single ionized sulfur, red indicates doubly ionized oxygen. But one of the things I want to point out, so the first thing is it's creating the heavy elements that are so important, but in the center here is a neutron star that's spinning about 30 times per second, okay? And it's got a wind, and it's driving material from the material surrounding the star into the area around it. And what you're seeing in the fingers that are going in is the Rayleigh Taylor instability. And we're going to talk about that a little bit more later. It turns out that that's important in the formation of stars, which is only known recently. Okay? One more reason that massive stars are important. So the universe began with hydrogen and helium about 380,000 years. We have the universe becoming neutral and transparent. That's where the Big Bang radiation comes from, the cosmic background. And it's not till about 400 million years that galaxies and quasars are forming, stars are forming, and we have the epoch of reionization. So it's thought that these first stars that are forming here, again, because they have a tremendous amount of radiation, are reionizing. So massive star formation, understanding massive star formation is important to cosmology as well. So let's talk about what's going on in the interstellar medium of our own galaxy and of all galaxies, and maybe at the beginning of the universe. So
hey, Dennis, could I pause you for a question real quick?
Please, yes. Oh, I didn't hear you.
There we go.
Okay.
The size of the neutron star in the crab.
Neutron stars are typically about 10 kilometers across. So the size of Washington, D.C. is the way we think of it, okay? And that's governed by the physics of neutrons. So it's a pretty standard sort of number with a maximum, trying to think what the maximum mass estimated is, between 2 and 3, I think, solar masses. And the wind stuff is relatively new. One of the things I enjoy, I don't want to bore you with my long history, but I've been away from the field for a while, and one of the things I enjoy about teaching is saying, you know, when I learned it, it was this, but now it's this. And so pulsar winds are a relatively new thing. The pulsar, by spinning quickly, drives a wind into the surrounding medium. So stars form inside molecular clouds. I know I've seen some of the great pictures you guys all take. I wondered if any of you have taken a picture of darkness. You see in the lower right-hand corner here, it's a particular cloud, I think this is Barnard 68 or something. But to illustrate how light can really, the dust can really block the light. And here's a picture of the Milky Way at the top, and you see all the dark spots. The gas and dust between the stars. I remember when I was a kid, my father would always tell me about how, you know, space was a vacuum, and then I became an astronomer. I thought, no, it's filled. It's filled with 1 particle per cubic centimeter, the particle being an atom or an electron. So the molecular clouds, however, are dense. And what do we mean by dense? 300 molecules per cubic centimeter. What's important to note about this is the temperature of the typical molecular clouds here are about 10 to 30 Kelvin. Okay, 10 to 30 Kelvin above absolute zero. The interstellar dust itself are soot-like particles. We're not especially interested in them. The other thing is to look at the composition: 70% hydrogen, 28% helium, 2% heavier elements. So when we talk about the first stars to form, they're really not going to have those heavier elements because the universe starts off with hydrogen and helium. So how do stars form? It's a battle. One of the words that physicists use is wind, meaning which physical effect is going to dominate. And so here we have the competition between gravity and pressure. So if the thermal pressure is bigger than the gravity, you keep a gas cloud, you don't form a star. But if the gravity is strong enough, it can convert the gravitational potential energy into thermal energy. But now we've got more thermal energy, right? And that wants to push away. So how do we get rid of that? Well, in our own galaxy, we form molecules. And those molecules can emit photons that go away from the cloud, taking the excess energy away. But we're going to see that And in massive stars, this is not quite so simple. The other thing you might notice is that typically when I draw a picture like this, it's a spherical. There's the old joke about the physicist and the spherical cow. Well, we really do approximate just about everything we're doing here as spheres, and it's going to turn out that that's important too, that we can really do that when we talk about massive star formation. So here's a picture from the textbook I use. What does star birth look like? Something causes a cloud to begin to collapse. Perhaps the explosion of a nearby star, but I showed you the radiation-driven model where it was just the radiation of a massive star. So something causes it to collapse. With the collapse, the temperature of the central region of the cloud rises, and the contraction then stops. Because of conservation of angular momentum, the cloud will spin and flatten. The dense cloud center becomes a protostar, and one of the things I learned in preparing the material for this talk was how important the protostar is. When I talked about this before, I always thought of the protostar as just sort of a name. You know, yeah, it's a protostar and then it moves on. But the protostar, again, in the formation of massive stars, turns out to be really important because it continues to grow as its gravity attracts nearby material. And the growth will stop once the material is all used, or the radiation pressure from the protostar blows the remaining gas away. And my favorite part, the core becomes hot enough for sustained fusion, and a star is born. So that's what we mean by a star. It's got sustained fusion because it's radiating here, you know, in the protostar. But it's called a pre-main sequence star. We're going to talk a little bit about the Hertzsprung-Russell diagram. Now, what I showed you before was a theory. Do we have confidence that there's some reality to that theory? When I saw this picture in the textbook, I thought, wow, what a great simulation. No, it's a real picture. I couldn't believe it first time I saw this. It's from a telescope looking at millimeters, submillimeters. It's a disk. It's in the textbook. It's used to illustrate planet formation. So in the gaps here in the disk, where planets are forming almost certainly, there's a particular star. But the point is, our fundamental understanding that the cloud will collapse into a disk, we don't have any question about that anymore. It's quite clear. We have the picture in front of us that shows us that disks really do form. And it's pretty straightforward in terms of conservation of angular momentum. So here's a Hertzsprung-Russell diagram. I really honestly don't like the way in astronomy we name so many things after people. So if you're going to discover something, be big about it and give it a name that helps people understand it rather than naming it after yourself. So instead of calling it the Hertzsprung-Russell diagram, we could call it, for example, the luminosity temperature diagram or the luminosity color diagram or something like that. But no, it's the Hertzsprung-Russell diagram, which helps no one understand anything. So here in step one, a protostar assembles from a collapsing cloud fragment. That's what we've talked about. It's concealed because of the shroud of dusty gas. We saw that picture of the really dark cloud. And it's going to move onto step two as it shrinks. Gravitational potential energy is converted to thermal energy. Surface temperature will rise. Radiation becomes the dominant mode of energy flow from within the protostar. So you see over here in step three, it's still hanging around the main sequence. I should have talked a little bit more about the Hertzsprung-Russell diagram. It's a plot of the surface temperature here versus the luminosity. And you see the luminosity is a log scale, as is the surface temperature. So the luminosity is going from 10 to the minus 5 in terms of the sun. Here's the sun at 1. So it's going from 10 to the minus 5 to 10 to the plus 6. So it's going about 11 or 12 orders of magnitude in luminosity. The temperature is going by about a factor of 10 from 3,000 to 30,000. And just as an aside, the reason for that is the radiation will go like temperature to the 4th power. We're not really going to talk about that. The point is the star evolves, this protostar evolves, and when the fusion, so here's the sustained fusion that I was talking about before, the fusion rate increases until it balances the energy radiated from the star's surface. And now it's gotten to the main sequence. A star like the sun will sit on the main sequence for about 9 billion years. As we move up here and increase the mass, the lifetimes are much shorter. They're burning it, you know, up to 1 million times as much luminosity as the sun has. Let's take a look at that, in fact. Let's ask what happens. Let's ask if we can figure out how the luminosity might change as a function of the mass as we go from this luminosity of one solar mass. I'm trying to remember what I did with my notes. If I took 6 here, no, I think I only took 5, okay? 5. So we have a luminosity of 1 to 10 to the 5. We should write that maybe as 10 to the 0, right? And we have a mass of 1, again, 10 to the 0. Well, on this particular diagram, it doesn't show you what the mass is, but a star around here would have a mass of about 20 solar masses. So big, it fits into our bimodal scheme of, more than 8. So it's definitely a massive star. It's not up to the 100 solar masses that we talked about in the opening picture. So we could do something a little bit silly. One of the fun things about astronomy is that the data in general are so bad that you can really make simple order of magnitude estimates because anything we can learn is helpful. So we could do a simple calculation and ask, how does the luminosity depend on the mass? By just saying, what if there's a straight line here between a mass of 1 and a luminosity of 1 to a mass of 20 and a mass of 10 to the 5. And I believe I did it, let's see. Yeah, so you could take the logarithms and you can do the stuff. And if you do that, which I recommend, you'll find that the luminosity goes like mass, depending on how sloppy you want to be, anywhere between 3 and 4. And then it turns out, of course, that that's borne out by calculations when they do simulations of what stars. So this is important to remember. The luminosity of the star will go like the mass to the 3rd or 4th power. And you can see that's roughly right because I'm going to, multiply the mass by 20 and I'm going to increase the luminosity by a factor of 10 to the 5. So if you want to take out your calculators and do logarithms and powers, you'll see that that's about right. I'm trying to remember if I put the exact number in. I think I got 3.85 when I actually used I used 20. Okay, so as the star gets more massive, the luminosity is going to go up greatly. When we're talking about massive stars, one reason I enjoyed the title was I hadn't thought about it again much, but they're only about 1% or less of the stars that we know about. So here's one star between 10 and 150 solar masses compared to 200 stars between 0.08 and 0.5. Here's our sun somewhere, at about 1. So in terms of number, they're a tiny fraction of the total number of stars in the galaxy. But as we saw in the first few slides, they have tremendous influence on the evolution of the interstellar medium, on star formation in general, on the galaxy itself. Now, to talk about radiation pressure, I don't know if you've ever seen this picture. This was dubbed Sunjammer by its designers. It's a NASA object in honor of a 1964 Arthur C. Clarke story of the same name. He coined the term solar sailing. This particular project, I like the picture, was killed in 2014, but NASA has something called the Advanced Composite Solar Sail System plan. So why am I showing you this? To illustrate that photons can move things, right? This is serious idea of having satellites that explore the surrounding medium around our own star by hooking them up to very large sails and being propelled by the radiation pressure of the sun. And I asked, and I was told that I could do algebra. So we're going to do some. We're going to derive something called the Eddington luminosity. And again, our sun is relatively dinky compared to some of the stars that we've looked at. And so you can imagine these more powerful stars could do more powerful things. So let's see if we can calculate that. And remarkably, again, something named after a person. It's the Eddington luminosity. So if you're first to do it, you get. Eddington was a brilliant guy. I'm not saying he doesn't deserve it, but we can do it in about 10 minutes. So imagine we have a photon traveling along, and let's go through some material of a density rho. And the photon has some intensity. We're not even going to worry about what the the dimensions of the intensity are. It turns out that they're a little complicated in real life, but we can just think of it, the informal understanding that you might have of that word, intensity, will work. And so you ask yourself, as the photon enters our material here, what happens to it? You know, it's going to be blocked by the particles in it. And what's the change going to be? So I'm going to use a little delta I to say, what's the change in I going to be proportional to? Well, it's certainly going to be proportional to the intensity itself, right? Because if I have a bigger beam, maybe more photons, I'm going to lose more photons. So it's going to be proportional to that. It's also going to be proportional to the length. Let's say that we go through some length, S. Right? So it's going to be proportional. If I go farther through, I have more opportunity for the particles to knock photons out of the beam. And it certainly is going to be proportional to the density. And if I have more particles in this medium, there's a greater chance that the photon runs into one of the particles. And so the change in the intensity is going to be proportional to that. And now, what we do is we want to replace the proportionality here by an equal sign. What do? We put some constant in. We're going to call it kappa. Kappa is the mass absorption coefficient. This is all we needed. This is all the physics that we needed right there, right? This is just a factor that's going to let the left-hand side of the equation equal the right-hand side. And so the physics is really in here, right? Determining that number, which we'll get to in a minute. By convention, by the way, they usually put a minus sign there because the material taken out of the beam, you want to call that positive. Okay, there's a whole bunch of obviously I simplify things. There's some validity concerns about how we did it, but what I told you is basically correct. So now one question we might ask is, we don't even know what I is, but we can determine what dimensions kappa must have, right? Because here we have an I, and here we have an I, and so whatever dimensions they are the same, so we don't have to worry about that. But what that means then is the dimensions of these things all have to go away, because the dimensions of the I's on both sides of the equation have to be correct. So for rho, the density, we have a mass, and we have a volume. Let's use centimeter cubed. And the length is going to be centimeters, the ds here. So that centimeter is going to cancel out one of those centimeters. So this is a mass per centimeter squared. So kappa must have the inverse of that. It must be centimeters squared per mass, which is going to be a gram, of course. All right. So there we have the physics of a beam going through material. And we're hiding it all in this term kappa. Let's continue. Let's now define a quantity called flux. And the flux is going to be the energy per time per area. The luminosity of an object is the energy per time. I'll write time as delta t there, because we always measure it. And so for a star, at any given distance from a star, the flux is just the luminosity over 4 pi r squared, right? That's the surface area of a sphere. So if you think about it, what's going on? We have a star here. We would go out to some distance r. And the material, the photons from the star are being spread out over this surface. And the area of this surface is 4 pi r squared. Now let's imagine some mass sitting somewhere in the radiation field of the star. We have more room to write, okay? Can we use the flux to write an expression for how much force there is on the mass due to the radiation? So the first number, if you remember, in the equation we had for the flux, we had energy. Right? Flux was energy per area per time. Well, it turns out that energy for photon can be written as the momentum of the photon times the speed of light. That's a simplification of another equation, but we won't worry about that. It's just P times C. So now we can write the luminosity, remember, was the energy per time. So we'll write that as P times C. We'll use our delta T again. We're measuring. Time is never a single thing, right? I have to measure it at one point and cut it off at some other point. It's a chunk of time. And so the flux then becomes P over delta T. By the way, I'm happy to make, I'm writing on a PDF. Happy to make the PDF available to you afterwards if you're not taking careful notes. And C over R squared. That's the dimensions we have of the flux now. But if you remember from your basic physics, P over delta T is a force, right? Because F equals ma, but in some more modern textbooks, they write it as the change in momentum or the change in time. If mass isn't changing, right, it's m delta v delta t. That's acceleration. This is ma. So when we see momentum over delta t, we say there's a force there. Oh, so that's cool, because that's what we want. Remember, we're trying to calculate the force from the photons on our little chunk of mass, or on the solar sail that we had. Again, there's some assumptions going into this. But if we look back at our expression for flux, I can now write, I'm going to write this as the force per unit mass. That's really the acceleration. So force per mass, right, equals F. There's the F. I'm just going to multiply that. Remember our friend kappa? Remember kappa had the dimensions of, I want to say centimeters squared per gram. So we're going to take our flux, multiply it by kappa over C, and that's going to give us the force per unit mass. So we took this expression here in the box, and we had to get rid of the R squared, because that's a cm squared. So we multiplied through by kappa, and again, the physics is buried in kappa. So the physics, kappa describes the interaction between the photons and the material. And so we see we have an expression here for the flux. We throw the kappa in, and we're going to get the physics of that interaction. Again, there's some assumptions that we won't bother going into. So the question we want to ask is this force F, is this, which equals kappa over C times F, is this greater than the gravity? And the gravity is just gmm over r squared, right? If normally it's that, but we did over here, we did force per unit mass, so this little m goes away. So with the original equation we had for the flux, remember there was an inverse r squared, and we can rewrite this, and I'm going to write it instead of forces. What I really want to know is mass over luminosity. And this equation turns out to be, this mass over luminosity, is it less than kappa over 4 pi gc? So we've got an expression here for the condition that will drive material away from a star. If L goes up, it will be less than this quantity, which I haven't told you what kappa is. It doesn't matter. It's some number. C is a number, G is a number, pi is a number. And so with really simple, straightforward physics, although I've hidden the physics in kappa, we have an expression. And now I cheated a little bit, because this is not actually the Eddington luminosity. If I want to write the Eddington luminosity, I'd have to put in an expression in for kappa. And I'll give you an equation now for the exact Eddington luminosity. It's 1.5 times 10 to the 38 ergs per second in terms of the mass of the sun. So remember when we looked at the Hertzsprung-Russell diagram, we figured out that m went like L, or rather I got it backwards. L went like m to the 3 or 4. So if I take this expression and I plug it into this L here, I see that this quantity on the left-hand side is going to go like m to the 2 or 3. So if m is 20, that's not too big. But if m is 100, what do I get? If it goes to the 3, I get a factor of 1,000,000, right? 100 cubed is 10 squared is 10 to the 6. So I drive this quantity on the left-hand side down by 1,000,000. So what does that mean? It means that my nice spherical assumption that I had before of the collapse of the cloud, the pictures that I drew, that worked just great in our interstellar medium for, 8 solar mass stars, maybe, for our 1 solar mass sun. We didn't worry about any of this stuff. But if we're talking about a star that's 100 solar masses, it's going to drive the mass that's falling into it away. So it creates a great conundrum. How does a massive star get to be massive? And one of the things that changed, this is what I do to my students all the time, but I'll do it here too. One of the things that's changed in the 20 or so years since I was doing this every day is computers. And so my PhD dissertation, I did a computer model of the interstellar medium driven by supernova. I did it by myself. There's just no way in the world anyone does a model like that by themselves anymore. There's teams doing it and using supercomputers and using very sophisticated codes. And that's what's required now to solve these sorts of problems. So,
hey, Dennis,
yeah.
a quick question. Why did you multiply the force by kappa over c halfway down the page?
This is the flux, remember, because I look at the dimensions and I got to get rid of, I want to turn it into a force. And when I looked at the dimensions, I'd say, oh, the kappa, which contains the physics of the interaction, so it's a legitimate thing to put in, has the right dimensions, the centimeter squared per gram, that will turn this flux, will give me the force per mass, which is acceleration. So another way to say it is I knew what answer I wanted, and I knew that was going to work. So I looked at it and said, is there a way I can argue for putting in kappa? And I think there is. I need the dimensions to work out. Kappa has the right dimensions. It does the physics that I need. It describes from our first picture, it describes the interaction between the photons and the material. So it's legitimate for me to do that, okay? And again, I'm happy to give the notes which go into maybe a little more detail. So if we look at the sun's luminosity, we look at this m over L here. If L goes like m cubed, let's see, what number do I want to look at? All right, what do you need to drive it over? What do you need to solve this inequality? Well, if L goes like m to the fourth, say, and it's 3.5, 4, something like that. It turns out that if m is only about 30 solar masses, the inequality is satisfied. And yet, I showed you in the first slide of the talk, a star that people estimate is at least 100 solar masses, or might be 200 solar masses. So this produced a great dilemma in the physics of star formation. And part of the answer, a major part of the answer, is in that Rayleigh Taylor instability that we saw back in the Crab Nebula. What is the Rayleigh Taylor instability? It simply says that if you have a heavier liquid on top of a lighter liquid, so the example that's usually given is oil and water, right? Oil floats on top of water. Suppose I reverse that. Suppose I put water on top of the oil. If I keep things perfectly smooth, they'll sit there. But as soon as I perturb it, the heavier liquid will drive itself into the lighter liquid. And you'll notice over here, there's a mushroom cloud. Because in fact, it's the same thing that happens with atomic bomb explosions. It's called Rayleigh Taylor. Rayleigh was the famous Lord Rayleigh. He came up with the idea for the static case that, one liquid sitting on top of another in gravity. But Taylor, G.I. Taylor, was a famous English fluid dynamicist, alive at the time of the atomic bomb, who came up with one of the solutions for it. And Taylor was the one who realized that in a nice, quiet static case, you have this instability, but you also have, if you drive a lighter liquid into a heavier liquid. And so that's the situation we have in the stars, right? There's all this junk sitting around it, trying to fall in. The radiation is pushing it back. So this lighter fluid inside, being driven by the radiation into the heavy liquid, you've got conditions for Rayleigh Taylor instability. And lo and behold, if you do a sophisticated three-dimensional simulation with a magnetohydrodynamic code, I'll look at the title of this paper, An Unstable Truth, How Massive Stars Get Their Mass. This is, I think, 2016, yes. What they're showing is that there's Rayleigh Taylor instabilities all over the place. This is a particular model. They ran a bunch of models. It's the first one it says lam, that means laminar. So they started off with a smooth surface at the center, and they produced a 40 solar mass star. When they made this star turbulent at the center, it went up to 60 solar masses. So they argue that what's going on is you take your smooth system that you started off with, and now you put reality into it. and it's not smooth anymore. The material is just not falling in. It's got these Rayleigh Taylor instabilities that lets the material kind of sneak in through the disk. We still have disk. And so the material in the Rayleigh Taylor instability can get in and build the star. In 2016, I think that was a major step forward. Let's go back. I said the talk was bookended by the Vale of Satellites and by my desire to learn about gamma ray burst. Here's the last Vale of Satellite being assembled in 1970, Vale 5B at Los Alamos. And one of the interesting things to me, I don't know, I think this is still the first generation Vale, but the next generation, the satellites, the people knew what they were looking for. They only pointed toward the Earth. So I find that really interesting, because if they had realized cleverly enough that what they wanted, looking at nuclear test ban treaty, was to look only toward the Earth, we might never have discovered gamma ray bursts. It was just by coincidence that satellites were looking for pi and saw these extragalactic bursts. So, as I said, the data were not secret, but it's only the people of Los Alamos really that had easy access to them back in the 70s. And here's the first paper in 1973. And so it was 1963 or 67 rather, we saw the first object, but the paper wasn't published till 1973. They obviously had other things to do. The paper was published in 73, but it looked at bursts from July 1969 and coincidentally July 1972. And here's the key thing about this abstract. Directional information eliminates the Earth and Sun as sources. Okay? So this is 1973. All we know is that they're not produced by the Earth or the Sun. The controversy over where they were produced by lasted for another 20 or 30 years. There were two groups. Are they local? Are they in our own galaxy, or are they extragalactic? So this is again a slide from Chrissa, which I really liked, but she looked at all the questions that one asks when you discover something like this. Is it a new astrophysical phenomenon? If yes, where does it come from? Is it nearby? Is it far away in our galaxy, or is it extragalactic? What are the durations and energetics? What progenitor star can make such an explosion? What are their central energies? We're not going to talk about any of this stuff. We're just going to talk about, is it a new astrophysical phenomenon? Well, the authors, that's that same first paper, they immediately thought of supernova. And I love the way they're arguing. If you're familiar with the famous line from UFO studies, it's absence of evidence is not evidence of absence. So that's what they're saying here. They're saying the lack of correlation between gamma ray bursts and reported supernova does not conclusively argue against such an association. So saying, well, we don't see any supernova, that doesn't mean they're not created by supernova. And then they also note the energy observed. Again, I love it. Not that it is consistent, but it's not inconsistent with the supernova as a source. And finally, I note, for those of you who are up on your Cold War politics, that they're at Los Alamos, they acknowledge the interest shown in the past by Edward Teller, who's informally known as the father of the hydrogen bomb. So it's good to know that Dr. Teller had some interest in the science as well that was going on at Los Alamos. So this was, what did we say, 1973. It took about 30 years before this connection between supernova and gamma ray burst was really established. Here's, I felt bad. This is a paper by a guy named Peter Mazaros. It's in Nature. And I was looking at another paper actually today, and they referenced somebody else. And I thought, oh, did I miss the reference? But the paper that makes the firm argument about this actually is after this. Mazaros must have had the information. And you see all this is doing here is showing that the gamma ray burst, GRB, right there, matches the shape of the supernova. So it's 30 years later we define that gamma ray bursts do come from supernova. It's going to turn out that there's two different types of gamma ray bursts, at least, the short and the long, as I said. It's the long ones that come from the massive star supernova. The short ones come probably from collisions of, we mentioned neutron stars, collisions of a couple of neutron stars. But the long ones are caused by massive stars. today we had our, Tuesday we have our weekly 1 hour meeting of the astronomy group. Today I learned about ultra long. So that often happens again in astronomy. We define things, we have two categories, and then something comes along and we have to modify. So I asked, I said, is there a, is there a definite, what do you mean by ultra long? There was no real definition. Is there any understanding? Is it a new class? Ultra long being 1,000 seconds compared to short is 2 seconds, long is 100 seconds, ultra long is 1,000. I said, is there, what do people know? Haven't enough of them have not been observed. There was some thought that maybe it's the population 3 stars. What are population 3 stars? Those first stars form, so we did that analysis of how stars form, but the population 3 stars, see there's again type 1, type 2, and now, there's a third type, 3. Population 3 stars are the stars that form at the beginning of the universe when there's only hydrogen and helium. These are the supermassive stars. Some people estimate that the mass could go up to 300 solar masses. They could be great tools to observe the distant universe, to observe that reionization epoch that we looked at. And here's a paper from 2018, and there's a couple of people who are really looking at this heavily now, which plots the star formation rate, basically. It's in solar masses per year per cubic megaparsec. Doesn't matter. The point is, it's looking at it as a function of z, which is a measure of the distance. It's actually a redshift measurement, right? Going back, here's us at z equals 0. Here's, I think, 20 is about that reionization time, the time when the stars and galaxies start forming. So we're talking about the very first stars going back here. And there's some thought that the GRBs, I won't go into the details of this because you can see there's a lot of details, a lot of papers are referenced. There's a lot of different ways to guess at the star formation rate. And there's some hope that gamma ray bursts will give you an accurate representation of what the star formation rate was way back when. This is a fit to the curve, 1 plus z to the cube. You can see plus 0.43, so not all that accurate. So the point is that understanding the formation of the massive stars can help us learn about the reionization of the universe, can really help us learn about cosmology. And this, again, from Krissa, so 3 takeaways from about GRBs. 1, they're extragalactic phenomena. I didn't talk about that too much, but as I said, there were great debates for many years. I was at NASA headquarters for a while. I can remember one of the guy who was on the losing side, the guy who thought they were galactic coming by and trying to convince me that they were really galactic phenomena. They are the most luminous explosions in the universe. They create black holes at their depths. And from my point of view, one of the most important things is number 3 here, having a better theoretical understanding of massive star formation will help our cosmology, because if we know when the first stars formed and how they formed and how they start to light the universe, we increase our understanding. So that's it. So I want to thank you very much for the invitation. In preparing for the talk, I really learned a lot. I have a much better focus on what I need to learn. It was interesting to know sort of nothing coming into this and feel fun. I asked an intelligent question today in the Astra group. Usually I ask dumb questions. So if I can't answer any of the questions you have, I'll be happy to go to the experts in my department and get answers for you. So thanks very much. Is there anything else I can tell you possibly about this subject?
All right, well, thank you very much, Dennis. Again, as I said in the beginning, at this point, if anyone has some additional questions, feel free to take yourself off mute and ask.
And like I said, I'm happy to make the slides and even my notes available if you want to look at any of this stuff in more detail, because I know I went pretty quickly through some of it.
I have a quick question. You talked a lot about radiation-driven
right. That's the big difference, yeah, between the low mass and the high mass stars.
And but you also mentioned stellar winds, and I'm just wondering how they compare to the radiation pressure.
The stellar winds are strong. I don't know a lot about stellar winds in general from the massive stars. I'm thinking the radiation has, a much bigger range. If I think of that picture of Cepheus B, it's the radiation that's clearly going across that long distance and melting, if you will, the cloud. If you remember the stars were forming in a place where the cloud really didn't look like there was any cloud left. And so that's an effect of the radiation from the star, not from the wind. That's a great question, though. I don't, so how in the, yeah, and it must be true even for the sun, right? Because they want to use these solar sails to drive things pretty far, and yet the solar wind falls off pretty quickly. If it were more intense at Earth, we'd be in trouble, though we have a magnetic field to protect us. So I guess my answer would be, yeah, the radiation goes out farther.
Thank you.
You're welcome.
So you mentioned the canceled project, but didn't the Planetary Society launch a similar project with a solar sail?
I think they might have. So I don't. That's a good question. I don't. The reference I looked at said NASA. You know, that NASA project was current, but I don't know how it interacts with. I don't know if the planetary one was before that now. Planetary Society one.
I think it was a couple years ago.
Yeah. So, but the reference I found said NASA was still working on the solar sail. That they had killed that first one, the one I had the picture of, but back in 2014, I think. But they're still working on one. Who knows? Rick.
Yes.
You just showed up on my screen, so I thought maybe you had a question.
No. I just
Okay.
was, I was just putting my camera back on. That was great, Dennis. I really enjoyed that. That was.
Thank you very much, Rick.
You're the expert. That's really nice.
I'm pretty far from the expert, but I'm learning. I'm really looking forward to spending the summer reading, and you know, I have a background in the education part of education. I headed the Teaching and Learning Center at the university when it was first created, and I tell students all the time about how they're supposed to learn, and that highlighting stuff doesn't really help you. And of course, what do? I highlight things. So I said, no, I'm going to finally do what I've been telling students, and what I've done is created a program to take the abstract of a paper and put it on a sheet, and then sit down with my computer here and try to take notes on the papers. And that's my goal for the summer, and see if I can get up to speed on some of these things. It's been really interesting to me. When you are up to speed, you can read a paper, you find the one or two things you need to know. But when you know nothing, you just have to sort of take it all in. So I have more sympathy for my students. In our astronomy courses, I taught astronomy and physics at the same time last semester. And it was really interesting to me that in the physics course, we start off with F equals ma. That gets us through about the first 12 weeks of the semester. But in astronomy, every week we're throwing tons of terms at them. And that's why I am sensitive to naming things after people, So I'm talking about the Hertzsprung-Russell diagram instead of the color luminosity diagram and things like that. So, yeah, so I'll let you know if these techniques I've been telling people about, of taking notes, work better than highlighting. But that's my hope.
I'll ask another question. So the textbooks, I guess, have for a long time talked about supernovas, causing compression of gas and initiating star formation.
Right. Still thought to be true, certainly.
Okay. So this is in addition to that.
Yes.
This process occurs.
Yes. And like I said, that was a 2009 paper, and they're going, oh, wow, it looks like this happens a little more often than we thought.
Okay. But would you say that the supernovae are still the dominant star formation instigators?
I think it's possible that they're not now, because in our galaxy there's about 1 or 2 a year supernova, I think, and there's a lot more massive stars hanging around. So it's possible that the massive stars are more important, or maybe equally important.
That's interesting.
Yeah. I'll have to find that out. I mean, that's a really good question, but I don't know if anyone really knows the answer to that. But one of the things in that paper I referenced that showed the Rayleigh Taylor instabilities that was really interesting to me is in one of the things they had to do to see how this would work is allow the star to move as it's forming in the cluster. That previous models, it's the sort of thing you do. Your first shot, you fix the star, right, and you see what's going on around. No, the star had to jiggle around a little bit. So when we talk about star formation triggered by these massive stars, there's some subtleties.
Very good. Thanks.
I thought that was great. Really crystal clear. You're a really good teacher, Dennis. I haven't heard you give a talk before, but that was
Very
outstanding.
kind of you, Rick. I really appreciate that.
Yeah, that was really super.
I worked hard. It was fun. It was really fun.
Well, I
You
guess
can
when you work
compare.
hard, it turns out effortless, right?
Right. That's the goal. Yeah, like I said, I've been told some people. I said I've been giving lectures for 40 odd years. It's the first time I have 10 and a half pages of notes that I wrote on the lecture. I never did that before, but I didn't.
It works.
I didn't want to miss. So, and it was really enjoyable for me, like I said, to integrate a little the stuff I'm hearing every day. Well, that's one of the problems with COVID-19. I miss my colleagues. It's when you're in the office, you have a question, you turn to someone and you ask and you get an answer. Now, at home, it's a little bit different to call them up and ask, a kind of a trivial, what you feel is a trivial question, the trivial answer. So things that would take 5 minutes in the office are taking me half hour, 45 minutes to figure out on my own. So there was an article recently, I can't remember where I read it, but someone said about this is hurting science because people are not getting the interactions that they need.
I think it really does. I mean, it just depends so much, I think, right? I mean, it's, I think a lot of us are finding this very, very productive and we're interacting with our group just fine. I think it's, obviously if you're doing experiments, it becomes a dead end at some point.
Yeah.
But I think so far, this has been.
Oh, good. Yeah. I mean, if I was in the middle of something, I can see that, but just trying to learn a lot, it makes it difficult.
I guess another way of saying it is, I really just don't miss anybody at work. I didn't say that.
I take it obviously Dennis is no longer your office mate.
No. We've been in touch, but it would be nice if we were. We could relive the past,
Yeah.
I've liked it too, Rick.
I'm sorry?
I've liked it as well, Rick.
Okay.
It's been very productive.
Yeah. Oh, yeah.
Oh, the other thing is you're home mostly by yourself. That's another reason it's productive. Right?
Well, I've got a part-time wife,
Yeah.
So
Sure what that means.
I guess Rick or Dennis, I mean, maybe do you want to shed a little light on what you guys were doing together 40 years ago?
There was a program called, I guess they probably still have it, Summer Students. And I was a student at University of Virginia. Where were you? Were you at Berkeley then, Rick?
Yes.
And so it was on the camp, and the National Radio Astronomy Observatory was on the campus. Was it on? Well, nearby the campus to UVA. And there were about a dozen or so students selected from all over the country. And so we were together. We weren't working together, but we were working at the same place in the same office, and we talked frequently. Yeah.
I think, Dennis, that your Faraday rotation paper is from.
Yes, absolutely.
Was that your first paper?
Yeah, my first paper, and believe it or not, it's still referenced occasionally. So.
Yeah, I think my first paper came out of there also with on the Interstellar Medium.
I didn't know you did work in the Interstellar Medium. Yeah.
Yeah, that's the radio transfer.
Oh, right. Yeah, radio transfer. Okay. Yeah. Who did you work with there?
Chunming Liang.
Liang. Yeah, I remember that name.
Yeah, those were. Oh dear, those are the days.
So I work with a guy named Tom Jones, and I still, occasionally I contacted him recently, and it was fun to catch up a little bit. So.
Yeah. Actually, are any of you familiar? I mean, a lot of you might be familiar with the Green Bank Radio Astronomy Observatory.
Yeah.
And either just from general whatever, or from the Almost Heaven Star Party, where they're very close to that and have excursions. So the Green Bank facility is primarily an observational site. Astronomers stay there, users of the scopes stay there, whatever. But it's a big campus. I mean, gigantic area with all these scopes, radio telescopes for observations. It's actually half of the operation. The other half is in Charlottesville, where the theorists are. And of course, observationalists can be there too, doing their data work. But so were Denis and I where it was actually Green Bank, but not Green Bank. It was the other half of the National Radio Astronomy Observatory in Charlottesville.
Do you remember we had to go out to Green Bank for like a week to give tours?
Oh yeah.
Yeah, I got in trouble. I never found out. I didn't find out at the time. I found out later because I was wearing cutoff shorts with holes in them or something. And
God
and
forbid.
some high-level guy came by and got all upset, and I found out later. Yeah.
Yeah, we had to give tours. Remember on the so-called Z-foot telescope? Do you remember that?
Yeah.
There was a
yeah.
2-foot radio astronomy telescope and millions of tourist visitors. So they would come and we would give the students would give demos on this cute little 2-foot in diameter radio telescope, which certainly picked up the sun. And you
I was going to say, I actually went on one of those tours. I was wondering if you might have been the one in the tour.
Oh, geez.
Were you the guy who complained?
And that's what I remember from it, was this little cute little radio dish that they swept across the sun, and you could static and go, oh, cool. That's
and it was.
what
Yeah.
it is.
Yeah.
And then he ratted you out about your shorts, Dennis.
Yeah, probably. So I guess the people who live there now, you still can't use cell phones or anything there.
Oh yeah, that's
Still a dead zone.
Yeah.
I had a friend who was involved with the public radio, and it took them, I think, years, if not decades, to get permission to create a public radio station in the Green Bank area.
Wow.
The quiet zone.
Yeah.
I hate.
Does that include no Wi-Fi?
That's a good question, because the Wi-Fi would certainly leak out of your house.
Yeah, I mean, a lot of people use Wi-Fi on their telescopes if they're doing astrophotography and that sort of thing.
Yeah.
They had us turn our DSLRs off.
Yeah.
Yeah.
Really?
And I understand everybody living in the vicinity can't use a microwave either.
Oh, really?
Wow.
Wow.
Seriously?
Oh, man.
I mean, they're not shielded well enough?
I guess there's got to be
in the basement or something.
or they're concerned about it.
You can pick up microwave radiation, microwave leakage with detectors.
Yeah, you can.
Boy. Yeah. Okay.
Yeah, I mean, I definitely don't know how they come to those regulations. The reason is clear in general, but I'm just speculating. I don't know, maybe if they allow microwaves and somebody's got like a microwave that's doing terrible leaking and there's no way to identify who it is, and what do? You start sending the astronomy police to people's houses? I really don't have any idea. I'm just guessing.
No, they've got radio trucks.
They got a radio truck that trades.
And can find that stuff within an hour or two.
Is that right?
My shortwave radio picks up stuff inside the house. Primarily, my refrigerator now is producing like RF in the, lower frequencies. But
so I can confirm that when I was a kid, we had our old black and white TV, and one of the channels would get fuzzy. We're getting it over the air, of course. And you'd walk into the kitchen and you'd hit the refrigerator and the fuzz would go away. Yeah. There was a problem with the butter dish, that separate container with the butter dish.
Oh, yeah. So I haven't done anything about the refrigerator yet, but I'm gonna have to.
Yeah, there's also I've read about folks who apparently are able to feel RF radiation, and so they tend to wander. They tend to relocate to the Green Bank area because they
really, yeah.
They feel better.
Encourage the Amish to settle there.
That they don't have to wear their tinfoil hats. Huh?
Yeah.
Cool. So, are there any other questions? Comments?
You should consider zooming in on some of our meetings, Dennis, if you want, just for.
I might do that.
Fun. Yeah.
Thanks. Yeah, if you have any questions come up, feel free to shoot them to me later.
Great.
Because it's an opportunity for me to learn. Appreciate it.
Any other final questions, comments in general? from anybody?
Bill, did you want to mention an AP Sig coming up?
Yep, we have the AP Sig meeting 1 p.m. on Saturday. Immediately the next Saturday. So don't have anything in particular planned yet. I've got a few possibilities lined up, but we'll be doing something. So, and you'll see a message go out over the groups.io as well as to APSig members.
Very good.
Okay.
Well, then, if there's nothing else, maybe we'll attempt again if everybody wants to unmute, and we'll do a little round of applause for Dennis. Dennis,
Yeah.
again, thank you very much. Very great talk.
Thank you
Thank
very much.
you.
Appreciate
That
it.
was terrific. Thank you.
You're welcome.
And then also an extended thanks to Rick for helping us find Dennis. So thanks a lot, Rick.
Yeah.
All right. Well, as always, again, a reminder, I am intending to put together a formal meeting for the third week of July, strongly leaning towards doing member mini talks. So if you have something you'd like to share, please reach out to me. Otherwise, a reminder that we are getting together casually every other, on the other Tuesdays, just to kind of chat and hang out and share whatever's going on. So those have been going pretty well for the past couple months, so encourage people to keep coming out for that. And obviously keep an eye and keep participating using the groups.io to, chat and share whatever else might be going on. So with that, we'd like to thank everybody for coming out and participating. And we'll see you next Tuesday.
All right. Good stuff. Thank you.
Thank you.
Bye.
Bye.
Bye-bye.
See you, everyone.
Thanks again
Have
for
a
the
good evening,
invitation.
everyone.
Guys.
Thank you.
Good night.
Night, everyone.
Set my leave meeting here. Okay, there we go. All right, guys. Good night.
Good night. Yeah.